we now introduce prime numbers. To define prime number, first of all, the prime numbers have to be greater than 1. So that's the first part of the definition. Now so we are going to consider n, integer n, to be the numbers greater than 1 first, okay? Greater than 1. Now, how do we define prime? It is for all positive integers, n is prime if and only if for all positive integers r and s, if r is equal to r times s, then either r or s equals n. So now, symbolically, that's what it is. So n is prime if and only if. By the way, I do not want to include that into the symbolic form because n greater than 1 is the kind of prerequisite for a number to be a prime. So I just focus on this part, if and only if. So by the way, n has to be greater than 0, okay? And now, for all, because we say for all positive integers r and s, so r, s in z positive, that means positive integer. If n equals rs, if n equals r times s for all the positive combinations, if n equals r times s, for n to be prime, then the following has to happen. Then either r is equal to n or s equals n. So in other words, then r has to be equal to n. When r is equal to n, s has to be equal to 1, right? So in other words, at the same time, this also implies s has to be 1. This or another possibility could happen. S is n, but r is 1. So that's how, when you see that, when n is r times s, and one of those happens, then you can conclude n is a prime. Now I would like you to try to negate this guy, give it a try. So let's try it. So that means n is not a prime, right? If and only if. The negation of for all means there exists r, s in z positive, such that if you remember how to negate if then, so let's quickly do a quick review. So P implies Q is equivalent to not P or Q. Oftentimes I use, if you don't freeze, I will shoot, when police yell, says, that's equivalent to say, freeze or I will shoot, right? So these two are equivalent. To negate that, this is the structure that we are talking about. So we are going to say P, which is n, equals rs. So the negation of this guy, the negation will be P and not Q, okay? So this is the P and this is the Q. So we have to P and not Q, right? You're going to negate this guy. So that means when you negate this guy, R is not equal to N. And S is not equal to N. So in other words, none of this is N. Then you can say this is not prime. Actually, this is how we define the an integer is composite if and only if. So again, we restrict our numbers to be greater than 1. So n equals rs for some integers r and s. So for some, that's why we say there exists, right? For some integers r and s, where r is not equal to n and s is not equal to n. That means s and r has to be less than n, so that their product is equal to n. So do you see that? This is actually the definition of this guy, which is the negation of the prime. So the negation of prime is the composite number. So they kind of like mutually exclusive, but they're negation of each other. All right, so now let's take a look at those are the two definitions. One is prime, one is composite number. Let's take a look at the next. Here is -3 a prime number? What do you think? Answer is no, because to be a prime we have to have n greater than 1, right? Because no, because -3 is less than 1, less than or equal to 1. That's not it. Let's take a look at another one. Is 16 a prime? And again, 16 is not a prime, because take a look at here, because we are able to exist. That means we can find, as long as we can find R and S, where R and S they're not equal to n, they're definitely less than n, so that 16 we can find like 2 times 8, right? We can find this is my R, this is my R, this is my S. You see there exists R and S, so that R times S is equal to 16, where R is not 16, S is not 16, or equivalently, R is less than 16 greater than 1, S is less than 16 greater than 1. So therefore we can say this is not a prime, because we can find this such R and S, right? Now 19, is 19 a prime? Yes, because 19 is equal to 19 times 1, and this is the only way, this is the only way to write 19 as a product of 2 integers, right? 2 integers. And you can see that if 19 is equal to R times S, here R is 19, S is 1, we can see that the only way to write this as a product, and one of those has to be itself, that's what it says. So either R or S has to be itself to be 19 in this case. That's true. So therefore 19 is a prime. Is every positive integer greater than 1 either a prime or composite? What do you think? I believe so, yes. And how so? Because take a look at how we define that. To be a prime and composite, first of all, n greater than 1, right? And do you see that composite is basically the negation of prime? So therefore, any integer greater than 1 is either prime or composite, because they're negation of the other. So yes, because the definitions of prime and composites are negation of each other, right? Negations of each other. So it's one or the other. All right, so this is the second part. We introduced prime and composites. Again, in the last 2 videos, we talked about even, odd, and prime composites. These are building blocks for the proof problems in this section. So it's important that you feel comfortable with these definitions.